All right, welcome to the Explainer. Today, we're dialing it way back to the 1960s to demystify the batch operating system. To really appreciate this seamless multitasking of whatever device you're using right now, it kind of helps to understand where it all started. And trust me, it wasn't always just tapping a screen to get an instant result. The whole history of operating systems is basically one long story of solving massively expensive bottlenecks. So let's jump right in and explore how early tech pioneers managed some truly heavy computational workloads.
Okay, let's dive into this. Think about our computing experience today. It's virtually instant, right? We've got graphical user interfaces, touch screens, and personal devices literally everywhere. But the 1960s? Totally different ballgame. There were no personal computers sitting on desks at home. Heavy computation was locked away in these massive, air-conditioned corporate labs. It was super restricted, used almost exclusively by giants like NASA or ISRO for really intense scientific calculations. You couldn't just open a laptop, type out a script, and hit run. The whole paradigm of how a human being interfaced with a machine was physical, manual, and highly exclusive.
Seriously, just imagine the physical labor required to execute a single simple piece of code back then. Step 1 meant loading your job offline onto punch cards or paper tape. Yes, you were quite literally punching holes in paper to represent your data. Then, step 2, you actually had to physically commute to the specific company lab where the mainframe was housed. Step 3, you'd hand over your precious stack of cards. And step 4, you just wait. It was this highly disconnected, tedious process just to get a machine to read your work.
And the crazy part is, you couldn't even interact with the machine directly. There was no command line or keyboard for you to use. Instead, you had to rely on a vital middleman, the human operator. You didn't insert anything into the system yourself. You just passed off your stack of punch cards to this operator, and they basically worked on a don't call us, we'll call you basis. They would let you know when your job eventually ran. It was a completely manual workflow where a literal human being managed the queue, not a piece of software.
So, the crucial point is, how exactly did this operator manage the absolute chaos of dozens of researchers handing them random jobs all day long? Well, that's exactly where the concept of the batch operating system comes into play. The operator's main gig was to physically sort the incoming stocks of cards, grouping similar kinds of jobs together into a single batch. They'd then hand this organized batch to the computer to execute sequentially. It was essentially a mechanical attempt at optimizing the workflow, trying to keep the computer focused on one type of task at a time so it didn't waste time constantly setting up new environments.
To visualize this, let's look inside one of these batches. We'll call it batch B1. The operator is physically sorting through the submitted punch cards, right? If they spot 2 or 3 jobs that are all complex Fortran calculations, boom, they group those together into this single batch. Then maybe batch B2 is something entirely different, like payroll processing. The operator would load the cards for batch B1, and the system would pick up the first job, run it, and once it finished, it moves straight to job 2. The whole idea was to keep that highly expensive CPU humming along through similar tasks without constantly reload it.
Makes sense, right? Sounds like a remarkably logical organizational system for the time. But here is where we hit a massive, massive wall. What happens when the CPU needs to read a file, access a peripheral device, or do any sort of input or output process right in the middle of a job? Sure, the job demands intense computation most of the time, but sometimes it needs to pause and read data from a magnetic disk or write out to a tape. When that happens, what happens to the flow of the batch? How does the system handle the interruption? Well, the answer is honestly painful. The CPU simply stays idle. It completely stops. And remember, running these mainframes cost hundreds, sometimes thousands of dollars an hour. If a job asked for input/output, that incredibly expensive processor would just sit there doing absolutely zero computation until that task was 100% finished. It refused to proceed to the next job in the batch. It just waited. This is what we call strict non-preemption. The current job literally holds up the entire multi-million-dollar processor until it's completely done. And this brilliantly illustrates why the multi-programmed operating system was such a massive leap forward. Contrasting the two, the older batch OS suffered from that brutal non-preemption. The super-fast CPU sitting completely idle during slow input-output operations. But multi-programming? It introduced random access memory, or RAM, to the equation. Suddenly, multiple jobs could be loaded into memory simultaneously. If job 1 needed to perform a slow I/O task, the CPU didn't just freeze, it would smoothly pivot and immediately start executing job 2. By effectively eliminating that idle time, multi-programming made the linear nature of the batch OS completely obsolete.
But man, back in the pure batch OS days, before multi-programming saved the day, the delays caused by all that CPU idle time were just staggering. Put yourself in the shoes of these 1960s users for a second. You drop off your punch cards, and the operator honestly couldn't tell you exactly when your result would be ready. Your return time might be a day. If the queue was backed up, it might be a week. For really complex calculations, it could literally be a month. And the kicker? When it was finally done, you had to travel physically all the way back to the lab, pick up your printed tape, take it back to your office, and just pray you didn't make a single typo. Because if you did, you had to start the whole agonizing process all over again.
Thankfully, tech moves fast, and things rapidly evolved to phase out those agonizing inefficiencies. In the early 1960s, manual human operators completely ruled the corporate labs. But by the mid-1960s, a major refinement arrived: monitors. This was huge because it began putting power back in the user's hands, allowing them to punch their cards more directly into the system and automating the job feed to the CPU. Then, fast forward to the late 1960s, and tech giants like IBM are formally launching robust, optimized systems like Fortran and the IBSS 7090X. These systems further automated the batching process and significantly sped up computations across the board.
Which brings us to a final thought I want to leave you with today. When you look down at your smartphone or tablet right now, executing thousands of concurrent processes, handling background downloads, streaming video, all without a single stutter, consider the journey. How do the ghosts of these 1960s inefficiencies still shape the blazing fast multitasking devices in our pockets today? Honestly, it was precisely the sheer frustration of watching a $1 million CPU sit completely idle that drove engineers to invent modern memory management, multi-programming, and the interactive systems we now take for granted. Solving the massive flaws of the batch operating system literally built the foundation of the modern digital world. Thanks for tuning into this explainer. Keep learning, and I'll catch you on the next one.